Ions related to weak acids or bases can themselves exhibit acidic or basic properties. Let's fill in this table so that hopefully you can get the idea of what we're talking about here. We're talking about the behavior of ions that are related to weak acids or bases and how they can exhibit acidic or basic properties. On the left you can see the first ion that we're going to deal with is the carbonate ion. The second column over, which is related to H2CO3, which is a weak. We know that carbonic acid is a weak. If we look at the third column, we're going to focus on how that original ion would behave. That is, the carbonate ion would tend to gain protons. And the last column, and would thus exhibit basic properties. Things that gain protons exhibit basic properties. Let's look at the next one. HCO3 minus. That's the bicarbonate ion, which is also related to carbonic acid. The ion, again, we're not looking at the acid, we're looking at the ion. That ion would also tend to gain protons and would thus exhibit basic properties. How about the next one? This is called the hypochlorite ion, and it's related to hypochlorous acid. The ion, ClO minus, would tend to gain protons, acting like a base. How about the next one? ClO2 minus, that's the chlorite ion, which is related to chlorous acid, and that ion would also tend to gain protons, acting like a base. You can see that most of these tend to gain protons, acting like a base, but the next one, NH4 plus, that's the ammonium ion, is related to the weak base, ammonia, NH3. If NH4 plus is going to do anything with protons, it's certainly not going to gain them, because NH4 plus, that is the ammonium ion, is positively charged, so it's not going to accept protons, it's not going to gain protons. If anything, it's going to tend to lose a proton, thus acting acidic. And the last one is the acetate ion, which we know is related to the weak acid, acetic acid, and that acetate ion would tend to gain protons, acting like a base. What we have here are some ions, all of which are related to either a weak acid or a weak base, and we can see that those ions tend to behave like acids or bases, depending on if they want to gain or lose protons. We should note here that the ions we're dealing with here must be related to weaks, not strongs. Thus, ions such as the chloride ion, or the nitrate ion, or the potassium ion, or the strontium ion do not exhibit acidic or basic properties. All of those are related to either a strong acid or a strong base, and any such ion that is related to a strong acid or base does not behave in the way we've just described. Because weak-related ions transfer protons, as I just mentioned above, strong-related ions do not, solutions of salts that contain these weak ions can be acidic or basic. It is perhaps ironic that ions related to weaks, not strongs, are the ones that influence pH. Your gut response would be to say, oh, ions that are related to strongs influence pH. The reality is that it's the ions that are related to weaks that influence the pH. Here's an ironic picture, a croc with a crock in its mouth. And this, of course, particularly hits home for me, as I wear Crocs all day, every day. For example, consider adding a spoonful of the salt sodium hypochlorite to water. The salt immediately does this. That is, it dissociates 100%. The strong-related ion, which is the sodium ion, related to the strong base, sodium hydroxide, the strong-related ion has no effect on proton transfer, but the weak related ion does in this way. That is, the hypochlorite ion will tend to gain protons. Incidentally, the water here has undergone the process of hydrolysis, where an H is split off from the water molecule, leaving a hydroxide ion also as a product. What we've produced here by this hypochlorite ion gaining a proton, we've produced some very weak acid, hypochlorous acid, but we've also produced the hydroxide ion, which is extremely basic. Therefore, we would expect a solution of sodium hypochlorite to have a pH greater than 7, that is, in the basic range.